In the previous video, we walked through an example where we knew the population standard deviations, sigma 1 and sigma 2. Or at least I claimed we did, and I made some up for the Buxton and Trout example. And we used the z-test to determine whether or not they were of equal speed. In this video, we're going to walk through what happens when we don't know those population standard deviations. And as I said in Chapter 10, this is most likely the case in practice. And so, like Chapter 10, we rely upon the t-distribution and the t-test. Unlike Chapter 10, our questions don't stop here. So we have to answer one more question about the sigmas. We need to determine if we think that sigma 1 is equal to sigma 2. Now, we don't know these values, but can we assume that the actual population standard deviations are equal? This can be a difficult assumption to justify. Sometimes it's reasonable, but we won't go too deep into it. But you should know that this is an ongoing discussion in statistics as far as how often we should justify or try to make this claim that these are equal. Now, there are some positives in terms of if you're able to claim that, that can help in certain scenarios. It makes the results fit very nicely with other statistical measures, and so there are reasons why we may want it to be true. And if we can assume it's true, then it's helpful to use this the yes side of this. But both of these are done, and so it's important to be aware of both of these. So in this video, we're going to walk through both scenarios, and we can see kind of the differences between these. To do this, we're gonna stick in the world of baseball, and we're gonna talk about the two MVP winners from the 2020, albeit shortened, but MVP winners nonetheless from this season. And so that is Freddie Freeman and Jose Abreu. So if you're new to baseball, there are two leagues, and so there's two MVPs. And so what we're going to focus in on is one aspect of being a good hitter, and it's not the only aspect, is how hard you hit the ball. That's pretty straightforward. It's probably better to hit the ball hard, and in fact that shows well in the data. And both of these players hit the ball quite well and quite hard. We have now data on that, and so we can measure how fast the ball comes off their bats. So we're going to look at that and see if there's any reason to think that these two players don't hit the ball the same with the same amount of power. On the face of it, you may not have a guess, and so we still will stick with our normal kind of two-sided hypothesis. So we'll be dealing with, let me just switch colors here. We're going to stick with, as I said, the two-sided hypothesis. So let's say that, and this will be the exit velocity, but we'll call it for Abreu, and is that equal to Freeman? Okay, and of course then that leaves us with the alternative as not equal. As we did in the previous video, we'll play around with an alpha of 0.1. And we'll go from there. So here's where we now identify the test statistic. And on the face of it, if you asked me to try to justify sigma 1 equals sigma 2, I'm not sure that we would be able to claim that. Well, maybe my default would be to say no, but we're going to start with the yes. Okay. So again, this determination is a complicated one, and it's full of nuance, and so oftentimes, when I ask you a question, I'll try to make it explicit in the question. But to highlight these two, we're gonna work through both. So let's first start with yes. Let's say that they come from the same underlying population standard deviation. If that's the case, what we're going to do is use what's called the pooled variance, and really eventually the pooled standard deviation in our calculation. Now, what does this pooled variance mean? Essentially, what we're doing is that we are going to get a sample variance from both of these players, the sample from both of these. And because we're assuming that sigma 1 is equal to sigma 2, there's really just one underlying sigma. And what we then have is two estimates for it. We have two samples, each providing an estimate for that underlying sigma. And so we're going to use both of those to try to get a better feel for where sigma is. And to do that, what we're essentially going to do is take an average. However, we need to take a weighted average because, again, with sampling, we don't have to have the same sample size. And so if we have, if we take a larger sample from one player, we should weight that sample as being a better estimate for the true sigma than the smaller sample. So we go through this process of estimating or pooling the variance to get to what we deem as a better estimate for that sigma. So that means we got to play around with a calculation, and that is as follows. Jump into a different color just to keep things straight. So we're going to do the pooled variance, so SP squared is, and here's where we're going to do that weighted average, taking into account a little bit of that kind of degrees of freedom feeling that we've been talking about with the n1 minus 1 and so on. So it's the following equation, but you can think of it as a weighted average, much like we covered in previous chapters. Okay, so we can plug those values in here, although I have not given you those values, I realize. So I've looked at their MVP seasons. I've pulled up the data, and we get well, we don't need the X bars yet. So let's just use what we need so far. So for Abreu, now I regret where I've put this stuff. Just move this up here somewhere. And I can tell you that for Abreu, there was an N of 182. Okay, and this is every time during the season that the ball went into play off of their bat. Okay, so there's an N of 182. We also learned that the S is 14.5, and for switch colors here. So N is 176 for Freeman, and S is 12.4. Okay, so I guess I could really label these as I did before. Though I wrote that really small. So, okay, and then I guess why don't I go ahead and just tell you that X bar for Abreu, going to be off the screen here, but it was 92.86. And I'll move this all. And for Freeman, that was 92.44. Okay, so already we can start to see that in our sample here that Abreu had a higher exit velocity. So if we find enough evidence, it's going to be that Abreu had a higher exit velocity or has a higher exit velocity, right? So if we do reject the null, it's going to favor Abreu. But let's see if we have enough. So plugging these values in, we get the following pooled variance. Okay, and well, now I don't have it labeled, but let's call it Breu player 1. So this is 181, 14.5 squared plus 175, 12.4 squared, and that is all over 182 plus 176 minus 2. Okay, and we're working towards that weighted average, right? We know it's going to be somewhere between 14.5 and 12.4. Because their sample sizes are pretty close in size, it's going to be close to the middle here. But we can go ahead and find this out for good. And 1.4 squared, I'm just plugging that in. Now, this is rather cumbersome, but it does, we're talking about whether or not something is significant, and oftentimes this comes down to a very close decision, and so we do want to be mindful of that. And okay, so I've plugged this in. You can double check this, but what I get for a pooled variance is 178.82. Now, I said it's somewhere in between, but of course this is the variance, and what we had listed were the standard deviations. So if we do, just for sake of argument, if we do take the square root of this, we do get, so this is SP squared, and so SP is 13.37. Okay, so that is in between and roughly halfway in between. So that makes some logical sense, right? We're taking the average of these two, again, because these are two estimates of what we are claiming is the same underlying standard deviation. And so both of them are just a sample of many samples. And so it's, because we've taken two, it's probably the best guess is somewhere in between. And so that's what we've done with the pooled. Okay, so now that we have a pooled variance, we can plug that back into our T equation. And it's going to look very much like our Z equation. So let me flip this over. Let's bring this with us. Okay, and just to refresh, we found a 178.82. So SP squared is 178.82. Okay, and so now we're ready to plug it into the T calculation. And the T calculation is as follows. Right, so again, we're looking at the difference between these two, and I should just switch to A and F. Again, if you're more comfortable keeping it as 1 and 2 and always remembering A is 1 and F is 2, or however, that is also fine. And now here, so I'm gonna write this down twice. Okay, so the most natural, what's the denominator of the Z? Remember, it is, for us, it's the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so similarly here, we have what we could write as SP squared over n1 plus SP squared over n2. Okay, we could write it this way, where we're putting that pooled variance in for each of the sigmas, because they're the same sigmas. Now, the way the book writes it, and what is often easier to just write down, is to factor that SP squared out. But I want you to see it in this form to realize that we're doing the same thing. And we're doing the same thing that we do every time we switch from that Z to that T. We put the S in for the sigma. And so let's rewrite this, the way the book has it. And of course, maybe I should have just stuck with the 1s and 2s because I cannot remember to keep that notation straight. The way the book does it is keeps that SP squared out front and then does 1 over N. There, I finally got back to the A. And writes it in that form. Okay, so we've just factored that SP squared out. So now, why don't we go ahead and plug these values in. Okay, I'm just going to switch colors to help our eyes out. So T is equal to, we found an X, so this was 92.86 minus 92.44. Okay, and on the bottom, we have square root of, what did we find? 178.82 times 1 over 182 plus 1 over 176. Okay, and so now all that's left to do is crunch those values, and we'll end up with our T score. Now, we did not, we kind of went out of order here because we're getting kind of comfortable with our process. Now, we said we're going to use a T test, and at a 0.1 alpha, we'll need to, of course, look up what that exact value is going to be, and by doing that, we'll need to calculate the degrees of freedom. Now, we've gone through this kind of cumbersome process of the SP version, and on the plus side, the degrees of freedom calculation for this is quite easy. So what do we get? We get 90. Okay, so 92.86. Sorry, I'm just plugging this into little Excel to double check my work. So up top here, we get 0.42 divided by 1.413 on the bottom. Okay, again, more than welcome to double check that. It's entirely possible. I'm off. But so what I get is a T of 0.297. Okay, so we should know probably just from playing around with T values enough that this is obviously not going to be significant. We're not going to reject the null. Now, for sake of our process here, we would need to find, so degrees of freedom is, in this case, it's quite simple. It's N1 plus N2 minus 2. And so we get, which we had show up in the SP squared calculation, but this is, let's see, 182 plus 176 minus 2, 356. Okay, and so our process, again, we've kind of done this a little out of order, but when we wanted to formulate the decision rule, we would then look at the T table, look up this column in the table, and look it up under the 10%. Okay, so and at this level, it's going to be almost back to the z-score, right? We're at a degrees of freedom up in the 300s, and so we're above the 200. It's in the second to last column. It's going to be nearly the 1.645. And so this is going to fail even that level. Yeah, and so that's what happens when we can assume, again, this is all under the assumption that we we can assume that this is true. Okay, so what I want to do next is just, or we'll do that in the next video so you can know when that's starting. But we'll look at the same process, but under the no condition.